This is section 5 of PLC programming from scratch. Now that we have a little bit of understanding about PLCs, about automation in general, about the different types of signals we'll be working with, we've learned a little bit about programming instructions, we're going to start putting those into practice and developing an actual program from scratch. The first step of creating that program is opening the RSLogix 500 programming environment, which we see on the screen now, and of course clicking on the New File button on the top left of the toolbar. That brings us up this processor type window with a list of all of the Allen Bradley PLCs compatible with this programming software. So we're going to program for the RSLogix 1400 Series B, which is the latest revision of the RSLogix 1400 PLC. That is probably one of the most popular lower-end PLCs on the market today. We'll go ahead and give it a name of PROC1 for processor 1, and down here where it says Communication Settings Driver, we have a choice of 4 different network protocols that we can choose from. Now where those come from is a separate program also made by Allen Bradley called RSLogix. And RSLogix is a program that is made by Rockwell to manage networks and connectivity between PLCs, HMIs, various types of servers, and we will get into this software in another section. But for now, it's just a note that this is where these choices are coming from under Communication Settings Driver. And we're going to go ahead and pick the MU500, which is the emulator driver. Processor node will be 1, and that's going to be our default node for any of these projects we're doing here because we only have one processor. We can go ahead and click on Who Active, and this brings up a smaller version of RSLogix, which shows us the different communication drivers that we have installed and configured at the moment, and it shows us if there's anything available such as processors or other devices that we can communicate with. And in this case we've got a RSLogix 1400 which is being shown as offline, and that's okay because our emulator isn't running right now. So we can go ahead and pick that, and that's going to be the network location that this program will communicate with by default once it's set up in time to download. So we'll go ahead and click OK, and now it brings us to a very familiar view. We see our project navigation pane on the left, which is already populated with Ladder 2, which is our default program. That is our main program, so I will right click on that, select rename, and go ahead and give it the name main. That way whenever we add other program files to this, we'll be able to look at a glance and know that is our main program file. So the first thing we want to do is we want to configure our controller. So we make sure we have our RSLogix 1400 Series B. We have the processor name that we put in, PROC1. And you see it gives us a little bit of information general about our program, that right now we have 3 program files. It says we have 9 data files, and when we look over here under data files, it starts us out with a file for outputs, a file for inputs, status, binary, and a few other data files, and of course we always have the option of adding as many more data files as we need of any type. When we click into controller communications, here we see our driver configured, so if down the road we need to change our driver such as going from a programming and testing environment into going to a live environment. This is where we can select and tell it we don't want to communicate on an emulator anymore. Now we would like to communicate on an Ethernet with an IP address. After we've set up our controller and we've set up our communications, we're ready to go into the next step, and that is selecting our I/O and configuring that, and that will be the topic of our next lecture. I'll see you then. Welcome back, everybody. Let's keep going and keep setting up our new program. In our last lecture, we started a new program and we configured the PLC a little bit. We gave it a name and we looked at the data files and program files that the program gives us by default to work with. The next thing we're going to do, after we already configured our controller properties, we want to come below there and double click on I/O configuration. And by now, of course, we all know what I/O is. We're all very comfortable with that term. And now we want to set our PLC and set the program up to interact with those inputs and outputs. So in our list on slot 0, and that's what this number is, we have our RSLogix 1400, and we'll go ahead and double click on that, and here is a little bit more configuration for our processor. The first thing we have to select is a base or type, and the RSLogix 1400 comes in a few different flavors with a few different bases. And in this case, we'll go ahead and select the BWAA base, and it'll be a 32 point because that's the only size that the BWAA base comes in. We'll go ahead and leave our series revision functionality type as A, and when we buy our PLC, of course, we'll select these various configurations and we'll know exactly what we're working with. Let's apply that and then click into the next tab, and we see embedded I/O configuration. As you might remember from the section on I/O, I mentioned that your more sophisticated PLCs don't generally come with I/O built in. All of the I/O you want to use has to be added on a module. The RSLogix 1400 is not such a high-end sophisticated PLC. It's a much more economic model, and it does come with some inputs and outputs built in. So for a lot of our inputs and outputs, there is some configuration required. In this case, we can set filters on our inputs which prevent jitter from signals coming in, and you can leave it at default, but typically you want to set your input channels at about 1 millisecond unless the device that you're using requires something else. On our analog inputs, we can select various frequencies for those, and in general we'll probably be using 60 Hz for most devices. Again, this is something that is going to depend on what country you're programming in, what type of electricity they use, and of course what type of device you're using. And in general, that's about the only thing we need to configure for slot 0, our PLC. To the right of this window, you'll see a lot of different devices, and all of these are input-output modules. And for this particular model of PLC, and for as far as this program knows, based on its most recent update, these are all of the I/O modules that Allen Bradley makes, which are compatible with the RSLogix 1400 Series B processor. To look at a few, some of the more common and more popular modules for a project, we'll look at an analog 4-channel input card, and we'll go ahead and add that to slot 1 of our project. And as soon as we add it, we'll go ahead and double click on it, and we'll see what kind of configuration can be done. Now, as that analog is a 4-channel input, that means it can accept 4 different analog input signals coming in. And this particular module gives us a healthy amount of flexibility as far as what kind of filtering we want to apply, and we had discussed filtering a little bit when we were configuring the RSLogix processor. So we'll go ahead and leave that at the default 60 Hz 450 millisecond update. Our input range, if you remember back to our discussion on analog signal ranges, I had mentioned that 2 of the more common signals were 4 to 20 milliamps and -10 to +10 volts DC. Here's where we make that selection, and this module can actually handle DC or amperage signals. So again, it's a very flexible module, and we'll go ahead and set this channel up to receive a 4 to 20 signal. And then our module is going to turn that milliamp signal into a numeric value that we can access from a memory location within our program and scale as appropriate and use in our logic. So in this case, we have 2 choices. We have raw proportional configuration, or we have a scaled for PID. Raw proportional is going to take the 4 to 20 signal and convert that into a range of 4,000 to 20,000. What that number represents, aside from the obvious correlation of 4 to 20, is a 14-bit signal. Now, a 14-bit signal is something that we'll discuss a little bit later, but that tells us what type of resolution or how many different levels we can read between 4 and 20 milliamps. If we select scaled for PID, we'll get a signal out that ranges from 0 to 16,383. And that is a number that's come up before, and I promised that I would get back to and we would mention again. And we're mentioning it now, but we will explain it a little bit further when we talk about resolution and bit depth. But this is the basic configuration for this type of module, so we'll go ahead and apply that. Some other modules that I would show you are, we have an 1762 IF2OF2 module. This has 4 channels total. 2 of those channels are analog inputs, and 2 of those channels are analog outputs. This time, this module gives us a choice of 0 to 10 volts or 4 to 20 milliamps. And the same raw proportional or scaled for PID signal coming in. Only we have 2 input channels and 2 output channels, unlike the last when we had 4 analog inputs. There are also digital I/O modules. Here we have a 16-channel digital input which requires no conversion, and as always, digital is quite simpler than analog to configure, to work with in every other way. We have relay output channels that can handle more than just a 5 or 10 volt signal, but can actually pass 120, 240 volts without arcing. And here are 2 more that are specifically designed for temperature sensor inputs. We have one for RTD, and we have another one for thermocouples. And of course, being analog signals, they require a little bit more configuration. So first, we have the choice of actually enabling or disabling each channel. We have several more options for the data format. We can even choose what type of thermocouple that we're going to be connecting to this channel. We have frequency filters, and we can even determine if we want to work in Fahrenheit or Celsius. So again, very, very flexible modules. And I won't cover the rest of these modules. Many of them are going to be self-explanatory, but it's good to know you have that kind of variety when you're designing a project and when you're writing a program. You're not going to have to spend money on a lot of channels of input and output that you're not going to use. You're probably going to be able to find something that fits very nicely to whatever needs you have. Okay, we're not going to put this off anymore. I've been threatening to give a more proper explanation of resolution and signals, and we're going to do that right now. So probably you've heard 2-bit, 4-bit, 12-bit, 16-bit, 32-bit, 64-bit. You've heard this term before, and a lot of people understand that the more bits the merrier. That means what? If you're talking about a video game console, it means the graphics look a lot sharper and more detailed. If you're talking about colors, it means they're going to be a lot richer and a lot more lifelike as the number increases. When you talk about a computer, you know that a 64-bit computer is generally faster than a 32-bit computer. Aside from knowing that more is better, a lot of people don't really know what those numbers represent, how they're calculated, and to most of us it's really not that important. But to a PLC programmer, it is important, especially when we're working with analog signals. Depending on the type of processor we're using, we're going to be able to process analog signals with anywhere from 10-bit resolution up to maybe 32-bit resolution on an input or an output channel. And what that really represents is how many different values can we extract out of a particular range. When we're looking at the RSLogix 1400 processor, we have 14-bit resolution. And 14-bit is calculated as 2 to the power of 14, which is 16,384. When we were looking at PID scaled values, we had a range of 0 to 16,383. Now you're thinking, why 383? I thought it was 384. Well, remember, the 0 counts as a value. So 0 to 16,383 is actually 16,384 levels. So that is our full resolution from that sensor. So when we have a sensor that is reading 0 to 100 degrees Fahrenheit, we can break that range down into 16,384 different increments. So if we scale that signal into a 0 to 100 value and store it into an integer, we are taking 16,000 plus levels of resolution, and we are limiting it to only 100 levels of resolution, because integers are whole numbers, 1, 2, 3. And from 0 to 100, of course, we only have actually 101 values. So we are throwing away a lot of resolution if we would take that value and store it in an integer. Now, depending on the process requirements, we might only need resolution to the whole degree. And if that's the case, it's probably smarter to do it that way, even though we are losing resolution. We are saving a little bit on memory. We're making it a little bit easier to work with and display down the road. So that might very well be the way to go. But depending on the criticality of that measurement, we might not want to be so quick to throw that resolution away. We can always store it in a float and then display it as a whole number if that's what's desired. But in case we ever do need a more accurate reading and a more precise measure of that temperature, we still have the float that we can go back to. Now, if we scale that value into a float with 1 decimal point, we have our original 100 levels times 10 levels given to us by the single decimal place, which gives us 1,000 levels of resolution between 0 and 100. And that is certainly not 16,000 levels by any means. We're still throwing away over 90% of our resolution. But it certainly beats 100. If we add a second decimal place, now we can multiply our original 100 levels by another 100 decimals. Now we have 10,000 levels of resolution. Now we're only losing a third of our resolution, and that is probably about the most balanced approach, because adding another decimal is going to put us far out of range, and we're going to be reporting levels that we couldn't possibly be reading. So we would rather be reporting less levels than we can actually read, which is going to give us somewhat of a more accurate measurement. So when we're scaling these values, there are a few considerations that we want to look at. First of all, we want to know what the resolution is on our PLC. How many levels do we have to work with? The next thing we need to determine is how much resolution do we actually need? Of course, we want to use most of the resolution, if not all of the resolution coming in, but in many cases that might not be necessary, and conserving memory might be preferable. On the other hand, if we don't use enough resolution, we might end up with a process that's too unstable. As always, it's up to the programmer to engineer appropriately a program and a system that meets the needs in the best, most efficient manner possible, without going overboard, without coming up short, and delivers a well-balanced solution. So now it might make a little bit more sense why our 4 to 20 milliamp signal is 4,000 to 20,000 when we bring it into our system. If you subtract 4,000 from 20,000, you get 16,000 bits of resolution, and coincidentally, that lines up nicely with our 16,384 levels of resolution delivered by a 14-bit system. If we tried to scale that signal to a simple 4 to 20 integers, we only have 16 levels of resolution. If we tried to display it as 400 to 2000, then we only have 1600. So the logical conclusion is we scale that to 4000, and that's something the PLC does for us when we're setting up our input channels. So if you understand the concept of bit depth, resolution, and how it applies to an analog signal, that is about all you will need to know about it for the extents and purposes of PLC programming. Congratulations, now you've got it. Now that we've covered our bit depth and resolution, let's get back into our programming environment and jump to the next part of understanding program setup. We know what our data files are. That's what holds our memory. We know what our program files are. That's what holds our ladder logic. What we haven't covered yet are our function files. Function files are inherent to the type of processor that we're using. Different processors and different manufacturers certainly have different types of built-in functionality. And for that reason, I won't go into great detail on these because chances are, if you start programming with a different PLC, you might not have any of this same functionality. But I will introduce you to a couple of basic function files in the RSLogix 500 environment, specifically when we're programming a MicroLogix 1400 processor. And the first one is HSC, which is high speed counter. And you see we have HSC 0 through 5, which correspond to 6 channels on the MicroLogix 1400 digital input, which can be configured to receive high frequency inputs. So we're looking for digital inputs which are pulsing at a very high speed, up to 20,000 hertz, and we want to be able to count those pulses for things like K-factoring, and we have to configure this because by default the PLC's digital inputs and even the input modules that you can add to the PLC aren't capable of receiving inputs that fast. It's just faster than the hardware is built to receive. And when we open one of these HSC files, we see a lot of configuration that goes on behind the scenes. Again, we're not going to go step by step through each of those. The manual for this PLC explains it just as well as I could in a video. But it is important to at least know that it's there, know that it's a possibility, and if you're planning on working with high-speed inputs, it's probably a good idea to consider purchasing a PLC which has that functionality built in instead of having to buy a high-speed module. The next function file we'll look at is STI, which stands for Selectable Timed Interrupt. And that is a very technical sounding term, and I will break it down into something that makes sense. What this function does is allows you to designate one of your program files. Right now we only have one, that's our ladder 2, but of course you remember from other programs we sometimes have 3, 4, 5, and 30 program files. This allows you to scan one of those program files more often than the rest, or to call it out of sequence based on some type of signal or some period of time that can be configured within this module. So if we need one particular program file, one particular ladder to execute at a specific time, regardless of the flow of the program, without needing to jump to it, this is the function that we need. So for some of the more high-speed operations, this comes in handy. And the most important function file, which is available on most PLCs, is the real-time clock. Now, older PLCs generally require a real-time clock module to be added to them, but our MicroLogix 1400 has that built in. And what that is basically a wall clock which runs inside of the PLC and can be set just like the alarm on your headboard. This allows you to program around time. So if you need something to happen every day at 9 in the morning, you can give your operator those set points on an HMI, and the PLC actually knows what time of day it is. I can't swear that the PLC keeps as good a time as your Timex, but it's good enough for process. As you can see, there are several more function files, and we're not going to get into most of those because they're things that you're not going to be using day in and day out. But if you're curious, of course, you can download a MicroLogix 1400 user manual online from ab.com for free. And it does a very good job of step-by-stepping through every one of these. It might be an interesting bit of research for somebody fascinated by PLCs, but in general, these are things that aren't going to help you from day one, and you're not going to be called upon to use in most cases. Now, the last thing we want to talk about in this section is our program files. And again, these are where our ladder logic is stored. We start off with ladder 2, which is provided by the program by default, and in lecture 1 of this section we named as main, and for a good reason. Ladder 2 is what this PLC is going to scan over and over again, and it's going to follow those instructions from top to bottom. So if we add any more ladders in our program files, the PLC will never look at them unless we tell it to specifically by giving it directions to go from main to jump to another subroutine, and then perhaps from there even to yet another subroutine, or more traditionally, we call all of our subroutines out of main. But for now, let's add some of those subroutines, also known as ladders or program files, by right-clicking on the program files label, selecting New, and it automatically gives us the next available number, and we should name these appropriately based on what type of logic we're going to put in them. Now, there are no firm rules as far as what you should call your ladders, what ladders you should have, how your ladders should be ordered, and in general, none of those things are really going to affect your program. When determining how many ladders to use and how to break them down, we look at a few different things like complexity of the program, size of the program, how much logic are we actually using, and the functionality of our program. It's probably not helpful to have a ladder with only one rung of logic on it, any more than it's helpful to have all of your logic in one ladder and to have 500 or 600 rungs of logic all in the same place. It might seem a little easier when you're creating the program, but if you ever need to go back and troubleshoot it or modify it, or if anybody else ever needs to pick up where you left off, they're going to have a very bad day. So let's consider some of the possibilities of different ladders we might want to add in a program. One thing we might know from the start, we're going to want some alarms. We're going to want to be able to call attention to anything that goes wrong in our process. So let's go ahead and set up an alarms ladder. And maybe we know we're going to be working with I/O. So let's go ahead and put an I/O ladder into this program. And alarms are great and I/O is important, but what are either of those without control logic? So we'll put one more ladder into this one, and we'll just call it simply controls. So now we have an idea of how we're going to break down our logic. This would probably work if we only have a handful of I/O and not a very complex process. But what if this process is controlling 20 pumps, 30 tanks, a filling station, mixing vats, boilers, and heaters that run several different processes each? Now, this breakdown might not make sense anymore. Now we might want to have 6 different controls ladders. We might want to have 3 different types of alarms. We might want to segregate our I/O out even further. So this is a very subjective part of the program, but what you want in the end is a program that's manageable. You want to be able to find what functionality you're looking for. You want to find where an input comes into your program. You want to locate an alarm very quickly when it's necessary. You want everything to be organized appropriately from the beginning, because for the rest of this program's life, the way you lay out your logic between ladders can either make everybody's work a lot easier or horrendous. That's completely up to you. Well, if you're still awake, this is the part where you tell me, Paul, that was not the most exciting section of this course. And I understand that, and I apologize, but it is obviously a very necessary step in learning how to program a PLC. The good news is it's over, and the better news is our next section is going to jump right back into programming. And now, instead of studying the instructions and setting up the program and learning how it flows, now we are actually going to start laying down logic, learning how to bring inputs into our process, and learning how to send outputs out. What you should have taken from this section is you should know how to set up a controller within a program, how to define a couple of ladders under your program files. You should have some idea about how to set up I/O and to list the different modules. That is going to be very important come the next section, because we're going to be assuming that we already have I/O modules set up, and we're ready to start addressing those modules and communicating with them and bringing data in and out of our program. So, as usual, this is the part where I invite you to look back through everything, maybe watch 1 or 2 lectures over again just to make absolutely sure that you're getting everything out of this course up to this point. Because from here on out, it's full speed and there's no slowing down for stragglers. So thanks for sticking with me, and I'll see you next section.